Today we will begin our journey into machine learning algorithms by studying linear regression. Linear regression is one of the oldest, simplest, and most widely used machine learning techniques. Despite its simplicity, it remains an extremely powerful tool for engineering analysis. Many advanced machine learning methods build upon concepts that originate from linear regression. Therefore, understanding this algorithm provides an excellent foundation for learning more sophisticated models later in the workshop. Many engineering problems require predicting numerical values. In pavement and materials engineering, we may want to predict variables such as watt depths, international roughness index, tensile strength ratio, or carbonation depths. These outputs depend on several engineering inputs such as traffic loading, environmental condition, material properties, exposure time, so on and so forth. The main goal of linear regression is to learn the relationship between these inputs and the performance output so that we can make accurate predictions for decision making. Linear regression predicts continuous variables from data. The basic idea is to find the best fit line that represents the relationship between an input variable and an output variable. In this example, exposure time is used to predict carbonation depths. The blue points represent observed data, and the red line represents the model prediction. For any new input value, we can use this line to estimate the expected output. In civil engineering, this type of approach can be used for any continuous variables such as carbonation depths, watt depths, international roughness index, dynamic modulus, compressive strength of concrete mixtures, or splitting tensile strength, so on and so forth. This slide explains what the model learns. Linear regression identifies three important items: the direction of the relationship, the magnitude or the strength of the relationship, and the overall trend in the data. A positive slope means that as the input increases, the output also increases. For example, longer exposure time may increase carbonation depths. A negative slope means that as the input increases, the output decreases. The key takeaway is that linear regression captures the general trend between the input and output variables. Now the question is, how does the model find the best line? There are many possible lines that could be drawn to the data, but linear regression selects the one that minimizes the prediction errors. These errors are called residuals. A residual is the difference between the actual value and the predicted value. The best fit line is the line that makes these residuals as small as possible. This is why linear regression is often associated with the least squares approach. This slide shows the full process of training and prediction. During training, the model learns from historical data. It could be data on anything related to your project. First, we provide past observations with known input and output values. So linear regression is a sort of supervised learning. Then the linear regression model learns the relationship between the input variable and the output variable. Once trained, the model can be used for prediction. For example, if a new pavement or material system has an exposure time of 25 years, the trained model can estimate the expected carbonation depths. This is the basic machine learning workflow. Learn from historical data, develop the model, then predict new cases. So far we have considered one input variable. So in the previous example we had one input variable which was like exposure time, and one output variable, and the output variable was like the carbonation depth. However, most real engineering problems involve several variables at the same time. Multiple linear regression extends the same idea to multiple inputs. In this example, tensile strength ratio is predicted using air binder content, web content, aggregate absorption, moisture conditioning time, traffic loading, so on and so forth. So the model combines these variables using regression coefficients to estimate the output. This is more realistic for pavement engineering because performance is rarely controlled by only one factor. After developing a regression model, we need to evaluate how well it performs. This slide shows three common performance metrics: R squared, mean absolute error, and root mean squared error. R squared tells us how much variability in the output is explained by the model. Mean absolute error measures the average prediction error. Root mean squared error also measures prediction error, but penalizes larger errors more strongly. In engineering applications, we should not rely on only one metric. It is better to examine multiple metrics together. So linear regression has several important strengths. It is simple, fast, interpretable, and easy to implement. These advantages make it a useful starting point for engineering analysis. One of its greatest benefits is interpretability. We can directly examine the coefficients and understand how each input variable affects the output variable. Because of this, linear regression is often used as a baseline model. Before using more complex methods, it is useful to ask, can a simple linear model already provide acceptable performance? Despite its strengths, linear regression has limitations. It assumes that the relationship between inputs and outputs is linear. This can be problematic when the true relationship is nonlinear, as shown in the example. Linear regression is also sensitive to outliers, and extreme values can strongly influence the fitted line. Another limitation is that it may not perform well for complex systems with strong interactions among variables. In pavement engineering, many processes are nonlinear, so linear regression may sometimes be too simple. This slide shows how linear regression can be implemented in Python using scikit-learn. First, we import the required library, then we create a linear regression model. Next, we train the model using fit, where xtrain contains the input variables and ytrain contains the known output values. Finally, we use predict to estimate outputs for new or test data. The important point is that the Python implementation is very straightforward, which makes linear regression a good first model for beginners. So let's summarize the key points. Linear regression starts with engineering data, uses input features, fits a linear relationship, makes predictions, and evaluates model performance using metrics such as R squared, mean absolute error, and root mean squared error. It is simple, interpretable, and useful as a baseline model. However, we must remember its limitations, especially when dealing with the complex or nonlinear engineering data. Linear regression is often the best starting point, but not always the final solution.